Good morning, everybody. Today we are going to finish our discussion of Chapter 15. The last section that we cover in Chapter 15 is 15.5. So, in other words, we are going to entirely skip sections 6 and 7. If we take a look at the Moodle page, you'll see that today this is lecture 23. And we'll have homework submitted. I'm going to change this due date if you are watching this in 2019 so that the homework will not be due this Friday, but rather next Monday. So we're going to start talking about the PowerPoint lectures, and we're going to begin this would be slide number 60, and there's only a few slides that we're going to cover in this presentation. So if you're orienting yourself with the PowerPoint attachment that's on the Moodle page, begin with number 60. All right, so what we are talking about here in three-dimensional motion is something that's called the Coriolis effect. And some of you may have heard about the Coriolis effect, and the main example that's given of the Coriolis effect is not true, but it's interesting for the sake of discussion. The Coriolis effect is often cited as being the reason why water in a toilet goes either clockwise or counterclockwise. Now, it's not, because it's not big enough. But basically what we're discussing is the idea that the Earth rotates, and if water has a tendency to flow either straight or through a rotation, that it's going to tend to rotate according to whether you're in the northern hemisphere or the southern hemisphere. And also, of course, then the theory would be that on the equator, water would run straight down a toilet and would not swirl at all. But the Coriolis effect, as it's discussed in life, is that in the northern hemisphere, the toilet water rotates one way, and in the southern hemisphere, it rotates the other way, due to this induced acceleration or induced rotation based on two rotating frames. But it's not true. The reason is because the velocity of the water is so small compared to the velocity of the Earth that it doesn't really have an effect. And the other reason is, most of the reason why the water swirls is because of the way that the toilet bowl is designed, and it swirls to keep it cleaner. So if it ran straight down, you wouldn't have the cleaning effect as if you have a swirl. So there are actually imperfections that are cast into the toilet bowl that create that. So now you know more about your toilet bowl than you probably want to, but there you go. That's the other part of being an engineer. We just, no trivia is small enough for me, so we'll go from there. So when we talk about the real Coriolis effect, what we're talking about is if we have a fixed reference frame, and within that reference frame, we have a rotating reference frame. Okay, so you don't even really have to think about the fixed reference frame, but like the Earth rotates. So the rotating reference frame might be the Earth. You can consider some particle P relative to rotating in the rotating frame. And so the absolute velocity then is going to be a vector product of the rotating reference frame and the particle within the frame. So in the past, we've separated out velocity in terms of translation and rotation, and now we're talking about its relationship to the frame and then the motion of the frame itself. So the Coriolis effect is a product, literally a vector product of that rotation. So if we consider this idea of the variable omega, and I'm trying to figure out what they did here. They used something funny. Okay, it's okay. We can do that. They just introduce omega basically with no pretense at this point. But if we talk about the idea of omega as being omega cross q as being the velocity with respect to of the frame with respect to the fixed frame, so the rotating frame with respect to the fixed frame, we can then say that the velocity of a particle is going to equal that rotation, that omega, crossed with the vector r, plus the first derivative of r with respect to the rotating reference frame. Okay? And then they go ahead and they abbreviate OXYZ as just being the scrolly F. That's like an old-fashioned F. So they're just changing the subscripting at that point just so they don't have to keep writing capital OXYZ. Okay? So capital OXYZ is the fixed frame. Capital O with a minuscule or small XYZ is the rotating frame. Okay? So if you go back to this equation then, you can just say that if we want to have the absolute vector, whatever it is, whether it's a velocity or an acceleration, in the fixed with a particle with respect to that fixed reference frame, but it's in a rotating reference frame, we can consider it that same vector of the rotating frame plus the Coriolis effect crossed with that vector. So it's just another way of splitting up that motion. All right, so then we talk about the motion or the velocity of some particle p. So we can say that that's going to be the omega crossed with the r plus the r dot with respect to the rotating reference, within the rotating reference frame. And then at this point they just change the subscripting in order to simplify it to p/scrolly f instead of o small xyz. We're still referring to exactly the same thing. All right, so then if we want to find the absolute acceleration of the particle, we need to take those pieces into consideration, work out the cross products, and we come up with the absolute acceleration is going to be 2 times that omega vector plus, or crossed with the r dot vector, or it's actually a radial velocity vector, and it's equal to this value just with the change of subscript. And that is called the Coriolis acceleration. So sort of the punchline of this slide is that if you have a particle moving without a change in velocity in a rotating reference frame, and you have that, and that rotating reference frame is being viewed within a fixed reference frame, that there's actually an acceleration of the particle that is induced by the frame rotating within the frame. Now, there's one example that I don't know if you can, sometimes people can kind of feel this in their stomach. And back in the old days, they used to do these at carnivals before they deemed them too dangerous. But basically, the example would be, let me widen this out a little bit. They used to have a thing called a double Ferris wheel, which basically there would be a bar here, and a wheel over here, and a wheel over here. So this wheel would rotate, and this bar would rotate as well. So you can kind of see that if this is rotating and this is rotating this way, that you're going to decrease your velocity of this point with respect to the fixed reference frame. So like somebody's here watching you, scared to death that you're going to die because it's a very dangerous ride, too many moving parts. But then if you're over here and you're moving this way and the bar is moving this way, that you're going to look like you're speeding up. So if you take you as being a point, your velocity at different points is physically going to be different, even though your velocity in the frame never changed and the velocity of the frame never changed. So that's kind of the deal with the Coriolis effect. And I hate to talk about the toilet scenario because it's a really good description if you think about it. But if you think about this, the bar is rotating at a speed, the wheels are rotating at a speed. If you take a flush toilet sitting on the earth and the water is running at this very low rate and it's on the earth and the earth is rotating in space at a very fast rate, the difference here is just not going to be significant. You're just not going to find any measurable change in the velocity based upon the toilet because it's just not fast enough. All right, so if we then take a look at slide number 61, we just continue this and we talk about the frame of reference in this general motion. And in this case, once again, we use that terminology where capital O, which is the origin, XYZ is that fixed frame. And now instead of a rotating frame, we just have some translating frame, which is A, because we translate now, so we don't have the same O, but we have X prime, capital X prime, capital Y prime, capital Z prime. So in other words, we've taken the fixed reference frame. Oh, you can't see this. I apologize. Let me pull this back over here. So we have OXYZ, which is the fixed frame shown in the light black line here. And the frame itself, we move to this point where O translates to A, and every point on the x-axis translates with the same RA vector, direction and magnitude, to some point on the x prime axis. Similarly for the y prime axis and z prime axis, we get a translated frame A, x prime, y prime, z prime, and then we can rotate, we can translate and rotate that frame to A, little x, little y, little z. So in other words, we're breaking up this sort of a weird general motion into a pure translation and a pure rotation, which we've done in the past when we just had particles on a slab of potato. All right, so if we take that then with respect to that original fixed reference frame and then consider that with respect to this translated frame, we get some vectors, and then we can find that point P. Then we also have to add in the Coriolis effect once we rotate it. So first of all, we translate OXYZ to A, X prime, Y prime, Z prime, all capitals, so all translation. And then we add that to the rotated frame with the omegas or the Coriolis effect, and we get a complete expression for the acceleration of some point that has been translated and rotated from the original reference frame. Okay. Excuse me, I'm going to sneeze. If I do, I apologize. Pardon me. All right, so we'll just take a look at how this works. And really, in the real world, we talk about double Ferris wheels, and we also talk about flushing toilets on Earth. Really, the place where this comes into effect is in machine parts, and so in pieces of machinery. So here, we have this disc that is mounted with this bracket onto this arm, okay? And we have a rotation here, and then we also have a rotation here. So we have a rotation about this axis, and then the wheel rotates. So this is a perfect example of where a Coriolis acceleration could come into play. So we want to find the velocity of this point P and the acceleration of P. We also want to find the angular velocity and the angular acceleration of the disk. All right, so I actually kind of prefer problems like this because you can work them out real strictly with vectors. So that's sometimes you'll get lucky and you'll see something. Like, I don't know if you remember, we had a problem where we had an axis tilted, and then we'd worked a problem before that, and if you just tilted the axis and considered that your z, the problem became pretty trivial. But that's kind of like waiting for a blessing from above. So we have to learn how to do the work, and then if a blessing comes, then you can run with it. But we can't count on a miracle to get these problems solved. So the best way to do it is with vectors. So we just go through the math. The velocity of point P is equal to the velocity of P in its own frame plus the velocity of the point in the moving frame, and the same with the acceleration. So then we find the angular velocity equation and the angular acceleration equation, omega and alpha. So they both involve that Coriolis value and also an omega value. So we go ahead and we write out our vectors. We have R, right, which is just right here. And then we have R of P with respect to A, which is the center of the disk. And then we have omega, which is going to be that rotation. Then we just plug into the equations and we find the velocity vector for P. So what we find is it's going to be equal to this value where we have omega 2 is on the disk and omega 1 is on the shaft. Now, another thing to consider, if this is the y-axis, this is just a kinesthetic thing, and this is on the x-axis, okay, and this is on the z-axis. The rotation here is going to be purely y. That means that the spin is going to be in the xy plane. So if we look at omega 1, it's always a j, right? Because it's on the y-axis, and our omega 2 is going to be purely on the k-axis because the spin is on that axis or in that direction. Okay. And then last but not least, we just continue those. Those expressions, and we come up with a complete expression for the angular velocity and the angular momentum of point P. All right, do you guys have any questions for me? It's very complicated, and just leave the math. Just chase the math down the rabbit hole, and you'll be fine. I will not assign any tricky problems. I'll assign straightforward problems that emphasize working through the math. Okay?
So you have your like double Ferris wheel thing, right?
Yes, yes.
And there's like the point where like both the arrows are going against each other, so it's like
0.
moving.
Yeah.
Is there any point like that on this where like
Oh.
the rotations are like perpendicular? Kind of?
Well, you know, I don't see it. Let me think about this. Let's take a look at point P. I think that is just an excellent question. Let's just look at the motion of point P. The motion of point P is always going to be like this, right? So that's always going to be in the xy plane. Anyway, in other words, if we just look at the disk, there's no z-directional motion. All of the z-directional motion is going to come from the rotation of the shaft, isn't it? So those vectors are not, they're going to add together vectorially. So you're going to have all xy from the disk and all z from the shaft. So it would be a funny trick if it was. I think I'm going to say no. I'm going to say no. Okay, I know why I'm going to say no too. So let me write this out. Mathematically, exactly, because even the speed is going to equal the square root of vx squared plus vy squared plus vz squared. And these three things added together, because it's square, will always, each one of those will either be 0 or positive, so none of them will ever take on a negative value. So the speed is never going to be equal to 0, because we can't make that equal to 0 unless vx, vy, and vz are all equal to 0. And they can't because they're not adding together vectorially. So that's a great question, though, because there would be points like that on the Ferris wheel, wouldn't there? Because the axes are both coming straight out of the page at us from the way I've drawn it. So yeah, so like you're going to have a point where the bar is spinning the Ferris wheel this way, and you're on the other side. You're going to have it twice, actually, one on each Ferris wheel. Yeah, where your velocity at that instant is going to be equal to 0. It's a great question. I love it. And I've never had anyone ask that before, so there you go. All right. Well, gentlemen, that is it for today. So I will be here Friday. I'll put up the last 2 homework problems from section 15.5. I will change the due date to next Monday, and I'll be here to answer questions if you need any help. So, all right. Aside from that, have a great day.